fact that you can talk to people who have had some impact on your career, kind of listening to how they think, how down to earth they are, is just, great.
Welcome everyone. So this is our Back to Basics track, and we're going to talk about debugging. So here's the thing, maybe some of you have heard me say before, most programmers spend most of their time debugging. So first off, I'm really pleased to see quite a lot of people here who elected to come to this session today, because it's kind of I think it gets really overlooked how much time we spend debugging, how much it dominates the process of software development, right? If you think about how many lines of code do you think you can type in and have it work first time? Now, obviously, it depends what you're writing, et cetera, and how hard you're trying, but typically, like how many do you think you get right first time? You might be a much better programmer than me, but for me, I reckon it's like 10, maybe, right? It never works first time. How many lines of code can you change and have it work first time? I reckon that averages to less than 1, right? There's 2 parts to programming. There's bugging and debugging, typing it in and making it work, right? And we spend more time, way more time. In the keynote this morning, Bjarne said, I think, that he had a number of 10 lines of code a day for a good developer, maybe 20 or 50. It doesn't take all day to write 10 lines of code, does it? And we do other things as well as just typing in code, of course. But anyway, debugging totally dominates software development. Someone who can put things much more eloquently than me, Brian Kernighan. This is quite a well-known quote. You may have heard it before. Everyone knows that debugging is twice as hard as writing the program in the first place. If you're clever as you can be when you write it, how will you ever debug it? Now, very wise words. Obviously, what Kernighan is saying is keep it simple, right? You're not as clever as you think you are. And so just, give yourself that margin for error, keep it simple. But I think there's an interesting corollary of this, which is debuggability is like the limiting factor in how good we can make our software. Whatever your metric for good is, how fast it runs, how small it is, how quickly you can produce it. If you can make it twice as buggable, you can make it twice as good. Or to put it another way, you can't be a great programmer without being great at debugging. And I think you can't be great at debugging without knowing the tools that are available to you. So how do we debug stuff, right? There's lots of things we can do. We've got lots of dynamic checkers these days that are very good. We've got debuggers out there. We've got fancy logging things and stuff. But most people, most of the time, just write printf, right? That's what we do. You've probably seen this good old XKCD cartoon, right? It's compiling. Why is it compiling? Because we added a print statement and we need to rebuild it and rerun it to get that more data out, right? And I think we do this, I think the psychology of this is quite interesting. I think we do this because it's kind of our safe place, right? If you've read Thinking Fast and Slow, the System 1 automatic and the System 2 effortful, as humans, we go to great lengths to avoid spending effort, like even mental effort. And if we've been programming for 20 years, you've probably spent 20 years typing in lots of printfs and rebuilding and rerunning it. You can just do it in your sleep. It's your happy place. It's the programmer's kind of make work equivalent of reading email or something, right? So I'm going to split the talk into 2 parts, general advice, and then we're going to get into just look at a bunch of the tools. This is not a tutorial, so the intention is not that you come away from this actually knowing how to use any of the tools that we're going to look at, but you will know that they exist, you will know the kinds of things that they do. Hopefully you won't be so intimidated, and then when you need them, you can go and look on the good old internet and find out how to do exactly what you need to do. But just knowing what's available and knowing what to use when is kind of the key thing. Actually, this is a C++ conference, so we're going to start at 0. So let's just think about what we mean by debugging. So I write my code, I have a set of expectations, and reality diverges from those expectations at some point, right? And the job of debugging is to track that back to that point, the point of that divergence. And actually, more often than not, it does something like that. And what we're doing is we're just building this jigsaw puzzle. We're getting clues as we go at a time. So if we're doing printf debugging, we're probably adding a printf, getting a new clue. state of the system that we didn't know, and then that often leads to more questions, and we run again, and we get more clues, and eventually we get kind of the aha moment, right? And so, two things I think make bugs hard. I said hard to fix here, really it's hard to find, right? Once we've found them, then usually the fix is quite easy. First is how long between the bug itself and you noticing, right? The longer that elapses, the harder it gets, the more state you have to track back through. And by the way, this is why assertions are so good, right? Because assertions they narrow that time between you noticing and the bug happening. The other, I think, kind of important metric here is how repeatable is it? If the program does the same thing every time I run it, I can just keep running it as many times as I need, and each time I bring out a different clue, and eventually I complete that jigsaw puzzle we just showed, right? But if it runs differently every time, maybe it only crashes one time in 100, maybe it crashes every time but in a different way, maybe it's not even crashing, it's just giving me bad results, and non-deterministically, we get kind of really hard when we get up into this right-hand corner. By the way, yeah, also the time between the bug and the failure, that's why bad results are the worst kind of bug to deal with, right? Because you might have a very long time. And then life gets really fun up here where we have the Heisenbugs. So as we add print statements or whatever we're doing to try and get the next piece of the jigsaw puzzle together, the bug goes away, right? Or fundamentally changes in some way. So the sand is sort of shifting beneath our feet. So it can get really hard. There are a bunch of tools available. There's no single, absolutely no one size fit all. There's even a place for printf debugging, just not nearly as often as it's actually used, I think. All right, so actually I was pleased in the keynote this morning that Bjarne had a bit of this kind of thing going on as well. I didn't rush back and write these. So different kinds of bugs. I think these are kind of the main classes of bugs. So logic errors. You could say every bug is a logic bug, but I mean specifically, like in the keynote today, less than when it should be less than and equals, and off by one error, that kind of thing. Pointer errors, we'd like them not to exist, again, as was discussed this morning, but fact of life in most real-world code that's out there. Error handling is a big one, right? So I don't mean actually really the absence of error handling. More often there is some code to handle the error, but it's wrong in some way. And the error doesn't happen very often, right? The file system doesn't usually just return EIO or something. Usually the read from the file system works, and so it doesn't get tested, and then the error handling code gets tested for the first time in production, like a lot of the time. And then you get a long time between the bug and actually the thing blowing up. So I have a bit of a rant that with error handling, it's better to panic most of the time unless you really do have a test case for it. Race conditions, we all know how horrible they are. Again, tend to be right in the top right corner of that chart I just showed. They're being non-deterministic by their very nature, and they tend to be these kind of silent killers. Something goes wrong and you don't notice for some time later. And a big one, I think, is interface assumptions. So I'll make a bad assumption about what that interface is going to return. So it might be interface to the OS, to the system. It might be an interface to another part of the code that I'm working on, maybe a module that someone else is responsible for. So I don't know, if I read from the file system and on Linux and I'm reading a file and I read 128 bytes, if 128 bytes are there in the file, they will all be returned. If then one day someone runs it with a pipe, with a FIFO, then it might return short. The read might return fewer than 128 bytes, and I need to go around and do it again. And I just didn't assume that in my mental model of the interface, and occasionally bad things happen. So those are the main ones I thought, but I just to make things a little bit interactive. Let's write. There must be some other good ones. What else can we say? Shout some out. All the categories. Yeah. Oh, that's so hard to type up here. Yeah. Conversions. Yeah. Do you know what I didn't say? I didn't say undefined behavior. That's a favorite. We all have an undefined behavior. It's a good way to show how smart we are. There's probably loads, right? We could carry on going, but it feels like no one's...
Different architectures.
Different architectures. Okay, so architectural differences, you get some memory ordering guarantees between that don't exist when you go over. Yeah. In a way, that's kind of interface assumptions, but let's... okay. All right. Let's get back on track. Okay, so finally to part one then. So some generic advice So the impossible happened, right? Well, except obviously it's not impossible. The impossible can't happen. So generally, it's an assumption, right? An assumption is something that you don't realize you've made. So we want to unpick, try and find where that assumption is. It's why so obviously this represents rubber duck debugging. Right? You may have heard the story. There was, I'm not quite sure where, but there was a computer science lab somewhere, and the professor noticed that every time the student said, I'm just really stuck, I've been struggling with this for hours, and here's the problem, la 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 la, oh, and in the explaining the problem, you realize the solution, right? So they said, well, let's put a rubber duck in the lab and go and talk to that. It's hard to talk to a rubber duck, especially if they talk back. So I think a better thing is, let's write it down. Now, hopefully it doesn't get anything like this. In fact, it usually doesn't. I think if you write it down with pen and paper, not typing it in, right? And the key to writing it down with pen and paper is that it's slow. It takes you longer to write with pen and paper. So you think more about what you're seeing. So I find very often I write down, well, what I'm seeing is completely impossible. There's no way ever that we could see A uninitialized when B has already, wait a minute. And that's a good form of kind of teasing out those assumptions. The other thing I just want to say as a kind of general point is, well, I said earlier that finding the bug is the hard bit and fixing it is easy, but often people don't really find the bug. They find the symptom and they fix the symptom. And I understand, we're under pressure. You know, the customer's screaming, we've got to get this thing fixed as soon as possible. The release is already 2 weeks late, everyone's shouting at us, so we don't want to go necessarily sort of fix things properly. But if you kind of go, yeah, well, you know, I don't know, this, like, just as a trivial example, this thing is null, it should never be null, just put a test for null, all good, the crash goes away. Yeah, but why was it null? And what else is hiding there? So this is what's sometimes called smelling smoke. If you smell smoke in what you're seeing, and when you're doing this investigation, make sure, if you possibly can, that you go all the way to the end, you fully understand. And I find that, I don't know, 50% of the time, what I first think, I didn't fully understand that, but I understand it enough, that fix will do. Keep going, and you realize, oh, holy shit, there's actually something much more serious and fundamental going on underneath this. The other thing is when you're looking, again, we're building this jigsaw puzzle, we're finding these clues, and sometimes you find, whoa, that doesn't look right. I didn't think that could happen. That's not directly related to the bug that I'm investigating, but I don't understand why that piece of state should ever be like that. Allow yourself to go on those tangents, because sometimes it is related to the bug that you're looking at, and even if it's not, you're just going to leave it for your poor colleague or your poor future self to stumble over some other time with no clues. Like, you've done half the work. You're already, you know, getting towards the answer here, so keep going. Don't leave it to someone else to repeat all that work that you've done. And then just had so many assertions that the code is like ugly and you feel dumb and stuff, but yeah, you just can't have too many, in my opinion, because of this time for the bug to the time that I notice that it's all gone wrong. And then finally, as I alluded to before, yeah, test or panic, right? So I often see code that has, you know, some error handling behavior for, yeah, I know the file system returns an error or something, and you say, well, there's no test case for this. Oh, I can't really test it. It's too hard to test. But could happen, so I want to handle that error. I don't think you should. I think you should just panic. Because if you haven't tested it, it doesn't work, right? And if by some miracle you haven't tested it and it works today, as the code changes, that code and the code around it and the callers and everything else, it will stop working, right, soon enough. So either, if it must work, if the error handling must work, make a test case for it, however hard that may be, otherwise panic. And then kind of meta, or piece of advice, or segue onto the bulk of the talk is, let's use the tools. All right, just before I get onto that, because I actually must be speaking too fast, I'm going slightly quicker than I'd intended. Any other bits of kind of useful advice from the audience? We've got lots of people who are way more experienced and way smarter than I am.
Question.
Yes, question.
Can you just clarify what you mean by panic in C++?
Oh, sorry, yeah, so question, well, can I clarify what I mean by panic? Yeah, abort, right? You know, or just, you know, raise the exception. Don't try and struggle on, just die. The program should just terminate at that point. And then you get a core file and you can kind of try and figure out what's going on. Yeah, Scott.
If you write things down, as you were saying, write things down kind of as you go, what you've tried, what you've done, what experiments, what results you have, you can share that with your coworkers and get either useful advice about, hey, go try this, what about this? Or sometimes they'll be like, oh, I think maybe your bug is this.
Yeah, right. So write things down and get advice from coworkers. Yeah, we see a lot of debugging happening like on Jira or GitHub or whatever your kind of bug tracking thing is, and people will place a comment and then somebody else will, respond to that, and you can make a collaborative process. Yeah, use the collective intelligence of the team. Yeah. Back there.
Yeah, so you mentioned print debugging, but I don't remember you mentioning logging.
Okay, so the question was, I've mentioned print debugging and I didn't mention logging. Well, I actually think of the two things are the same. What's the difference in your view?
I think that when you build a system, you necessarily are logging all kinds of details about it that aren't debug related per se, right? Like a connection between
Got it. Right.
database read, blah, blah, blah.
So I've got some log statements that I put, the log statements aren't really written for debugging a particular problem. They're just there so that I've got some kind of observability, I guess is the popular term for it now, right? That I've got some kind of sense of knowing what the hell the system's doing.
Using the log statements, for sure.
Yeah.
Look over the log and you look for anomalies, for example.
Right. So look at the logs, find the anomalies. Absolutely. I meant to say that. So what I think you usually get a process of the thing fails in some way, or now I've got something to debug. I look at the logs, and sometimes on a good day, I've got enough information in those logs to understand root cause. Oh yeah, there was, I needed to check for null or whatever it was there, and then often there isn't enough information in those logs, and we need to just keep going some indeterminate number of times to get more and more clues. So yeah, so logging, using the existing loggings there rather than just like add new printfs in. Absolutely. One more from memory. Yeah.
So you said panic first. So this is fail stop behavior. But in many deployed systems, you really don't want fail stop behavior, right? You want the thing to actually indeed soldier on and maybe just degrade gracefully, right? So it's not great if you have an application that just fails all the time and it's user facing.
Right. So I'm glad you asked. So the question was, so it's all very well to advise panicking, but in some systems you don't want to panic. It's not acceptable to panic. You want to actually soldier on and maybe degrade gracefully. My answer to that is, if that's the case, then you'd better have a test case that that's what happens, because chances are it's not going to degrade gracefully. The wheels are going to fall off and things are going to explode, and other bits of collateral damage are going to occur. So sometimes there's systems where panic is not an option. So like it's flight control software or something. So I hope all the paths are tested in the flight control software on the plane that I'm getting on. Yes.
So I use the write out all my thoughts in the logging Slack thread. But where that gets into trouble is sometimes you have too many thoughts and it's impossible for anyone to actually parse them all.
Yeah.
So I go back and I use strategic bolding so people who are reading it later will catch.
Okay. So you're writing down so you're writing down in the Slack thread or wherever with a view to first getting all your thoughts out and then structuring it in a way that somebody else can contribute. Yeah. And out of interest, do you ever find the process of structuring it helps you to realize you don't even need the help from somebody else, but that really is the equivalent of asking for explaining it to somebody else and having them spot it. So yeah, you're right. Writing it something that somebody else is going to read makes you write it more thoughtfully. Yeah.
More of a post-mortem theme, maybe you write a unit test for that. Once you find the bug.
Yeah, once you found the bug, absolutely you want to write a regression test for that. Yeah.
Just run further
and
just fix it, commit it, and you're done.
Yeah.
Sometimes it's worth to actually write down the post-mortem.
Absolutely. So full kind of post-mortem. It depends. In practice, it depends on the bug, right? So if it depends on what you're doing. So if you're doing it that so-called inner loop debugging, I've just typed the code in and it didn't quite do what I wanted. It's probably not practical to do a post-mortem in that case. But if something's I believe this is correct, it's deployed to production, and now it turns out it's not, there's some kind of escape, then doing a kind of post-mortem on that test escape, I think is a really good yeah, that's a really good thing to do. Well, although I would say, yeah, it's kind of that's post debugging, but important. And then also, I think you alluded to make sure that there's regression tests so that you only have to fix it once. All right, I think we better. I think I'm back on my schedule now, so we can crack on. Right, some tools. So many tools. So I mean. So by the way, I think I said very clearly in the abstract, but maybe not in the title. This is very Linux kind of centric. So I hope that is okay for everybody. But yes, so if you're running on debugging C++ code on Linux, so many tools today. Just let's start with the most obvious, GDB. We'll look at, we're going to look at these all briefly. LLDB, Valgrind sanitizers. Strace and ltrace are cool. There's the Libc++ debug modes, and if we get time, because I just always like to, we'll do a bit of time travel. Let me just, let's start off with good old GDB. So can I just see a show of hands, and keep your hand raised if you've used GDB in the last year? Keep it up. So that's most people, not most people. And now keep your hand up only if you've used it in the last month. Yeah, a lot of hands gone down. And last week? I mean, I know I've been traveling and stuff, but yeah. So it's usually what we see is this kind of spread of, most of the time, I think people break out GDB like tool of last resort, really, right? Or only in certain scenarios. And clearly, it shouldn't be a tool of first resort. There are lots of tools that we'll look at, and but I think it's often only when the printf strategy has really exhausted any chance of being fruitful. By the way, I'm going to do a little survey, and I'm going to repeat that hands up question for the different tools that we use, because I'm really interested to know. Obviously, we've got a massively skewed, biased audience here, right? This is not representative because you chose to come to this talk. Anyway, so what are we going to show in GDB? So I was going to show, I think I've got a little bubble sort program here. And so if we compile this, and I run it in GDB. So you can, let's just show a couple of things. I mean, everybody's kind of vaguely familiar with it, so I'm not going to go into too many details, but we can do start, which is just to put a temporary breakpoint on main and then runs up to main. I can go layout source so that I can actually see what's going on. Let's go, this is a version of the program that doesn't actually have a bug, so just a few next commands to step forward. I don't want to go over around this array all of the time, so I'm just going to type until, which is kind of like next, but just always goes forward. Let's have a look at what the sort program is doing. So I can do things like, now let's try and get the syntax right here. So I can display, so display is like print, but it's going to happen every time I stop at the prompt, and I can cast it. And so I think what I've got here is, actually, what do I have here? I think I've got a long, an array of long star. I think that's what I want to do. And no, that's not what I wanted to do. Undisplay one. Got that syntax wrong. Maybe it's like this. No. Oh, I had this working this morning. Anyone see what I'm doing wrong? Did that before. That's just that those arrays should be. So it's slightly weird. It's not proper C syntax, but it does what we want, I think. Yeah. So. That's so annoying. I can't think of how I did that before. Anyway, if you get I'll try and figure it out. But we can step through and we can watch. It's a shame. It's a nice little demo because it shows the bubble sort kind of trickling through the array. Whatever. Anyway, what else are we going to show? There's a nice thing called GDB dashboard. Anyone use GDB dashboard? I probably don't have enough pixels on this to show this in its best light. But it's basically and its own, there's a GDB init file with loads of good stuff in it. Yeah, okay. So, so if I start it now, so yeah, not really enough pixels here, but we can change that. So we can go dashboard, layout, and I just want to show the source, and let's show the variables. So now I've got a bit more screen real estate to work with. And look, so if I do this, break on sort, that's hopefully going to work a bit better. So now I can start to see, oh no, it's still not doing the right thing on my array. But you can kind of get a bit more of an interactive view, and you can look at the variables while you're stepping through and things. So, and it's very configurable, GDB dashboard. So it's quite cool kind of alternative to TUI mode. TUI mode, by the way, hopefully most people are familiar with that now. It's just better. I mean, I probably only use non-TUI mode if it's a really simple kind of investigation. So layout source is the easiest way to get into and out of TUI mode, so you can kind of see where you are. So there's so much stuff on GDB, right? And I've done various talks on it, and I haven't even exhausted it yet. There's more to do, just like sort of mix it up a bit. It's very rich. It's kind of fractal, I find. The more that I learn about GDB, the more I find there is stuff to know. The Python integration is very cool. Particularly the ability to do pretty printers. Oh yeah, that's what I wanted to show. So people often worry about C++ classes and things. So, but if I've got a really simple vector thing here. So, and by the way, -G3 is quite good. That can give you a bit more debug information. Makes your program slightly bigger, but it won't run any slower. Oh yeah, that's another thing I wanted to say. So people often get confused. So -G, to give you debug information, does not affect the code that is generated at all. Okay, it's just gives extra debug information in the binary format. So it won't slow it down. It won't change anything. It just makes it a bit bigger. So let's compile that. Let's look at that in GDB. So let's again use until to get this vector initialized. So I haven't done anything special here, and it's got these pretty printers already kind of built in, so it can tell me what that vector is. You can look at it without the pretty printers by doing something like that. There you go. So that's what it would look like if we didn't have the pretty printers. So ships with any modern system will ship with GDB by default. It's got Python pretty printers for the STL and for other things that you might want to look at. You will get into trouble if you are trying to, if you copy, I see this a lot, people, for whatever reason, we have complex environments, and you copy the GDB binary from one distro to another, and then you'll find often that it can't make sense of the pretty printers. The pretty printers need to be, so the pretty printers will be installed in your system, but you need to have then you get a version match between, so the pretty printers are basically Python libraries, and you get a version match between the Python interpreter that's in your GDB and the pretty printer Python libraries that are on your system, and the pretty printers either don't work or work a bit. So that's just a bit just something to be aware of. But generally that works very well. Probably the biggest thing, biggest complaint, let's be honest, biggest thing probably that sucks about debugging with GDB is optimized code, and it gets lost sometimes. And it's a bit sad that there's a kind of race between the compiler writers who are doing ever cleverer optimizations, and there's loads of people working really hard on that, and then there's one poor soul who's working on generating the debug info and trying to keep up. So it's usually that the compiler is not generating the debug info that the debugger needs. It should be able to do that. It's basically a bug. There's a paper about this that I saw the other day that is not considered a bug. The compiler writers definitely consider it a bug if they have some fancy optimization and the behavior of the code that's generated is incorrect, obviously. But it is not considered a bug if the debug info is incorrect. It's just considered a shame, right? And so there's this kind of, there's always this kind of race, and the debug info often's not up to it. But I think for that one, my advice would be, don't panic. So I think people often kind of say, well, that was weird, and then I stepped somewhere I didn't expect to go. Just step forward a few more, a few step highs or something, and you often find you get back to something that makes a bit more sense. You often see value optimized out. Again, step forward a little bit, often you'll find that value becomes live. So it's fiddly and it's annoying, but don't use it as an excuse not to use the debugger. Right? It still gives you a lot of power. Obviously, if you can build with like -OG or something, that's a nice. -OG is an optimization level that sort of deliberately tries not to defeat the compiler. It doesn't really mean much on Clang. Clang just aliases that to -01, I think. But on GCC, it does. It changes things a bit. We can attach to the running process. We can debug remote things. Dynamic printf is quite cool. So you can look at, these are all, actually the documentation for GDB also is pretty good. It's pretty complete, and it's mostly understandable. The trouble with it is, just like GDB itself, it's just not discoverable. So you have to know what's there and to know what to search for. But once you know that dynamic printf exists, which basically lets you do printf-style debugging without recompiling the code, it just puts a little breakpoint and then emits whatever you tell it to emit at that point. So you can add printfs without recompiling and rerun, which is kind of neat and pretty easy to use. And of course, there's loads of front ends for it, right? There's VS Code, C-Line, Emacs. A lot of people still use DDD. I was talking to somebody just yesterday who still likes using DDD. It's basically, as far as I can tell, pretty much unsupported for the last 10 plus years, but it has this really nice ability to draw out the data, right? It's called the data display debugger, and it gives you the ability to kind of draw out the data, and nothing else seems to do that. But anyway, so there's lots of different front ends to use, loads of power. You can just keep learning it forever. Before I go on to LLDB, anything really big that I missed on GDB, or that you disagree with? Anything I said that's wrong? No? Wow, okay. So, LLDB. Right, hands up. Who's used LLDB in the last year? Way fewer hands. Interesting. In the last month? Week? Well, it's probably slightly small sample size, but I'm not unsurprised to see that people who use LLDB seem to use it more. There's way fewer LLDB users than GDB users. Basically, nobody seems to type LLDB. LLDB is used by, most famously, Xcode, the Apple IDE, and other IDEs as well. Very few people seem to type it. Some people love it. It's really very, very similar to GDB in all kinds of ways. So let's see what that looks like. So LLDB, let's just run the same program again. It does not have a start command, but that's okay. I can break on main and run. And you see it looks very like GDB, and I can type GUI, and I get this thing. So, whoops, that was a bit slow. So maybe the GUI is a little bit nicer, except I actually think it's a bit of a shame. It doesn't have a CLI. And basically, most of the GUI front ends to GDB also don't give you a CLI. They seem to have this philosophy that it's either clicky buttons or it's typing, and you can't have both, and I think that's a real shame. I think that one of the nice things of TUI mode, and actually DDD, is it lets you type at the CLI and see the kind of graphical kind of representation of where the code is. But it does, it's got this, so we can, and it's got the help. So if I look at the help, it gives me some of the key bindings that I've got. So I think I can just N for next, so it's kind of, like all of between LLDB and GDB, it's the same but different. That's coming out of that. The big difference, though, with LLDB and GDB is kind of a software design philosophy thing. So GDB is basically a kind of parallel independent project to GCC. And by the way, GDB works just fine with code generated by Clang, and LLDB just fine with code generated by GCC, as we just saw there. But the design philosophy is because obviously the debugger needs to do a lot of stuff the compiler does. I can type expressions, it needs to parse those expressions, and I can even actually, I don't know if you can do some LLDB from GDB, there's a command called compile. I can either compile code and inject it into the process that I'm debugging. And clearly the debugger and the compiler are kind of mirrors of each other, right? The compiler's turning the source code into machine code and the debugger's doing the inverse. But rather than have these as like independent kind of sister projects, let's have a common project, and out of which, by pulling in the appropriate modules, we produce the debugger and produce the compiler. And I have heard claims, I haven't validated, but I've heard claims that it does a better job, LLDB does a better job on debugging sort of complex C++ templates and structures and things, which is kind of makes sense. So it's not something I've observed myself, but heard people say it. It's generally less complete than GDB, it's catching up. So the GUI thing that I just showed you has had less, I looked this up just before doing this talk, apparently it was done by somebody one rainy weekend, practically. It's kind of just, whereas the TUI mode on GDB's had quite a lot of love over the last, 10 years or so. So I think it's not as featureful, it's always kind of catching up, but it might give you better experience. And it does pretty much everything that GDB does, just like not as richly. So it's got all the Python integration. Again, just not as complete, not as rich. You can attach and you can do remote debugging and pretty much anything. You can load core files, all the rest of it. As you can probably tell, I don't really use LLDB. I tend just to type GDB because it's what I know, and I've got lots of scripts and pretty printers and stuff. But any comments from the room about LLDB and pros and cons? Was that a hand up over there? Yeah. So the question is, do LLDB and GDB use the same or different debug formats? Same debug formats, so they both read dwarf. And it's both version 4, version 5 coming, I think. So they're kind of, you do get quite good cross-compatibility. Yeah. Yeah, another point.
So as an advantage, I tend to find LLDB is a little bit more performant, quicker to attach, quicker to step, et cetera.
Interesting.
So that tends to be easier in our application, which is very multi-threaded network with queues coming in, and timing can cause it to sync fault if we don't go quick enough, right?
Interesting. Okay, so you'll find that LLDB is a little quicker, especially with a big, very threaded program. Yeah, I can believe that. GDB can be quite slow. Yeah, good. Thanks for that. All right. How are we for time? Okay. Hands up if you've used Valgrind in the last year. Ooh, quite a few. Yeah, last month, week. Yeah, okay, all right. Probably quite a few. I mean, a lot of people have it now, have some version of Valgrind like integrated into their CI and stuff. Was that, when people say they're using it, are they mostly using it in their CI or just like bringing it out and actually investigating a problem with it? Both. Yeah. So it's very easy to use. So I noticed it was still, I think, a minority of hands that went up on having used Valgrind. It was one where, I think this is the case for a lot of, actually, right. So a lot of these Linux debug tools are really good, right? And it's so easy for cynics to like shit on them and say, oh well, GDB doesn't give my variable optimized out, and Valgrind's like slow and la la la. And you can find all these problems. Sure, any cynic, it's very easy to be a sort of lazy cynic, and we can always find problems with all these things. But mostly, I think they work surprisingly well. And I remember the first time that I used Valgrind. I mean, must have been much more than 10 years ago. And I'd known about it for some time, and I hadn't dared to use it because it sounded magic. And therefore, if it's so magic, it's going to be horrible to use. It's going to be super complicated. I'm probably going to have to recompile my code. I'm probably going to have, and my code's really complicated. Is it even going to cope? And eventually, I got so stuck, and I'd done all the printfs that I could possibly do, that I thought, there's nothing for it. I'm going to have to take the plunge. I'm going to have to break out Valgrind and run it. And it was so easy. It just worked. I didn't have to do any of the scary stuff, all the stuff that was scaring me and putting me off. And I think that's the case for a lot of these things. So you just dive in, and it might not be perfect, but mostly these things have been developed with developers in mind, and have been a lot of energy has gone into making these things easy to use and well documented. So let's show it. So I have here, which version of Buffer? Yeah, so I've got a program that writes one past the end of the allocated heap. So if I run it, well, okay, got away with that, right? But clearly I only just got away with it. If I run it in Valgrind, oh, look, okay, invalid write of size 1 at line buffer.c, line 7 is 0 bytes after it gives me lots of information, very useful, very easy to use. If I've got something where I'm suspecting some sort of memory safety thing violation, then it's very useful. It doesn't do everything. Let's go back to my buffer.c. Let's do this one. Now, I've put this padding, by the way, because otherwise the program just crashes with stack smash if I don't do that padding. So I just added some padding. Yep, everything's good. Right. So it caught the malloc, caught the access of the end of the malloc. It wasn't able to do it on the static buffer because it doesn't know. It's kind of the big pro and con of Valgrind versus Address Sanitizer, which we'll look at in a moment, is I don't have to recompile my code for Valgrind. And clearly that's a big win in some situations. It does mean it runs more slowly, and it does mean because it's like happening after the compilation stage, there are things that it just doesn't know about. Maybe it could have figured that out from the dwarf info, actually. I expect it possibly could, but it doesn't try to do that. So actually, Valgrind is a suite of tools. So Valgrind tab is such, so the lack of discoverability, the best thing I think is tab. So of course you have to know. So tool, is it dash? So look, there's lots of, so Valgrind actually is a suite of tools. The default one is memcheck, that was the original one. And then these are, obviously there's some things that give you just the architectures that you can run on, but we've got these cachegrind, callgrind, there's hellgrind to look for race conditions, DRD, which is kind of data race detector, which is kind of an alternative thing, kind of doing the same job. So there are lots of things. So if you've got a suspected race condition, you can run it with hellgrind or DRD, for example. Cachegrind, I think, is more about performance optimization if I'm looking for cache issues. As I said, no need to recompile, just works. It is quite slow, but so it can't be used everywhere, but where you can use it, it can be very useful. Address Sanitizer is the new kid on the block. So it doesn't have a logo. All these tools have logo apart from the sanitizers, as far as I could figure out. So that kind of ruined my slides. But anyway, apart from that, and it's basically a compiler feature. So I do have to recompile because it's going to use knowledge of the compiler. It was originally in Clang, but it's been in GCC for some time. So fsanitize. So all this you can do with Clang as well. And again, there's actually lots of sanitizers. So if I tab. Lots of sanitizers, but the most famous one we're going to look at today is Address, and I'm going to run that on buffer. Now, so it's a compiler feature. So now the resulting a.out has all the checks in it. So now I just run my a.out, and yeah, okay, it's a little bit more colorful output, basically. But yeah, and remember, this is the version that doesn't have the malloc. This is with the static, and look, it's able to tell me exactly what's going wrong. Because it's a compiler feature, the compiler knows, right? So it can do a little bit more stuff, and it can run more quickly. Just for completeness, let's go back to the one that Valgrind did spot. We'll see it's basically the same. Okay, so here, buffer overflow. I think, did I forget? I forgot to do -G, didn't I? Yeah, so I forgot to do -G, so it doesn't tell me the line number, right? Because it can't. because I didn't tell it about the debug info. So I should have done that. And now it gives me line numbers. Okay. So yeah, so just like Valgrind, the sanitizers are a suite of tools. The main one's Address Sanitizer, Thread Sanitizer, Memory Sanitizer. Actually, there's a whole bunch, as we saw when I did tab. Basically a compiler feature. So it's way quicker at runtime. I think it depends what you're doing. Thread Sanitizer is slower than Address Sanitizer, but generally it's going to run like half speed, maybe, on a good day. Does use quite a lot of memory. But that's compared to Valgrind, which can be like 100x or something. So none of these things obviously are designed really to be used kind of always on in production. But when you suspect something, they're good things to turn on, and they're good things to run in your CI as well, just to look for oopsies that accidentally get committed. So yeah, all of these sanitizers look, actually there's not quite as many as it looks like, because there's an undefined sanitizer, undefined behavior sanitizer, which basically turns on all of these things. Yeah, undefined behavior is just like blows my mind how much undefined behavior there is, and that it's such a thing, to be honest. And yeah, undefined behavior sanitizer is super useful. I would definitely recommend that in your CI. You will find stuff. Good. Anything more on sanitizers or Valgrind? What did I forget to say?
At a guess, how much slower is undefined turning an undefined sanitizer?
Oh, how much slower is undefined behavior sanitizer? I have no idea, but you did ask at a guess, so I'm happy to guess. 2x? I don't know. Something. I mean, that's a complete guess, but I can't imagine it. I mean, it's going to depend what you're doing, of course, but it might be better than that, actually, because maybe it only needs to put in hooks and checks when you're doing dodgy things. Maybe that's a smell. If it's a big slowdown, probably yeah, that's a smell. Oh, yeah, hand up there in the back.
I looked it up. Oracle says 2 to 3x in here.
Oracle says 2 to 3x for UBSAN. There you go. Right. Sometimes it is right first time when you guess. Cool. I didn't do my poll. So hands up who's used Address Sanitizer in the last year, either in CI or, and I can't remember if it's similar people. Right, last month, last week. Yeah, okay. So interesting. I'm actually a little bit surprised that I was expecting more hands for both Valgrind and the sanitizers, because they're so useful. Peter, yeah?
I think that's probably because they're in, as you say, this continuous integration. So I'm not using them, but they get run once.
Yes. So they might be used a lot more than even people realize. I'd imagine, though, if they are in your CI, you would know, because sometimes you would commit some code and the CI would go,
I know they're there, but I can't say I've used them.
Yeah, right. So the question is a bit ambiguous, isn't it? Yeah, it's true. It's true. Yeah, yeah. Cool. For libc++, both for GCC and for Clang, you can define these macros that basically change. I've made these links, so you can look up what these do. Oh, I haven't got any internet. Nope. All right, that went weird. Hang on a second. So if you compile with these macros defined, then more checks will be done. So there's a lot of talk this morning from Bjarne about the importance of range checking, for example. So you turn these on, then a lot of range checking will be enabled. With GCC, so with the GNU, I guess it's not GCC, I guess it's the GNU Libc, then it's really just on or off. With Clang, you've got these just different levels off, i.e. not defined, or 0 or 1, which I think is just more checking but heavier weight. These are definitely good things, I would think, to be running at test time. Possibly a little bit of duplication with sanitizers, maybe, but I think it'll give you more useful information. They're all or nothing. That's the only thing. You can't compile some modules with this defined and other modules without, because the structures, the data structures for the STL libraries will change. They've got more, they carry a bit more state in order to do the checking. With GNU Libc, you've got these equivalents, so you can actually do these by hand. So rather than having the standard bit set, I can have the GNU debug bit set, and then I can have I can sort of opt in and out of individual data structures that checking if I want to. Hands up, who's used or uses that? Oh, no one. Excellent, so I could say anything I want and no one could contradict me. Hands up, who's used strace or ltrace in the last year? Oh, way fewer than I was expecting. Okay, right. I mean, I don't even bother with much. So that's not well used at all. Okay, so strace just gives me all the system calls that the application issues. And so for that first level of debugging, actually, can be really useful, because often it's like the system returned enoent when I tried to open a file that it expected to be there, and whoever wrote that code, they didn't do that. They have an attempt to handle the error, but not very gracefully, and that gets lost. And so I just get this completely meaningless error that comes out. So the thing you tried to do didn't work because blah. And actually, the real problem was this open failed enoent. And if they'd panicked, then I would have known what the problem was. So let's look at what that looks like. So you can just run it on like any old application. So here we go. So if I strace, so that's ls. And these are all the system calls that ls is doing. And I can see it going through the exec, and then break, and then does some mmaps, and then does some opens and reads and things. That's not kind of too surprising. And then down the bottom here, look, here's the write system call that comes out, and then here's where it displays the stuff that comes out. I can redirect that all to a file. That comes out to standard error, so I can redirect that. So I can extract it from the output from the program. A nice feature of strace is, or strace, is -k. So -k gives me stack traces on all of the system calls. So I can see who's making that system call. This is the ls on my system, right? So it has no debug info. It's not compiled in any kind of, this is just a release ls on my system, and it can still give me the backtrace, which is super useful. The other thing that's good with strace, by the way, is -f to follow fork. So strace f. So if I run, say, GCC, then GCC, of course, is a wrapper, right? And the actual compiler is called CC1, I think, or at least it used to be. And there's quite a few wrappers. And of course, the preprocessor runs and all this other stuff. And strace -f will follow fork. It will follow all of the children in the tree, in the process tree. So I can kind of see what's happening. I can attach to a running process strace -p. There's another thing I meant to talk about called pstack, which, I'm surprised that's not on my, I thought that was, okay. Which is actually a wrapper around, I haven't got a network, I'm not going to do it. But pstack basically will attach to a process and give me backtraces of all of the threads, like a snapshot kind of thing, right? So if something's stuck, I can pstack -p pid and see, and maybe the deadlock becomes clear from that. It's basically the same as doing gdb-p and then looking at the backtraces, but it can be useful for gathering information if I'm packaging it up in a bug report or something. In fact, it is exactly the same as gdb-p. It is just some shell scripts that run GDB in the appropriate way. ltrace is kind of the same as strace, but for dynamically linked libraries. So it'll just intercept all of the DL, the dynamic. So I can see my calls into Libc and malloc and everything. And you have to filter on what you want to see. With -e filter, so it gives me some examples down here of what that looks like. So like that. Oh, which version of buffer.c did I have? Yes, good, right, so. So that should, what did I get wrong there? Maybe it's, doesn't like that. Oh, well, that didn't work. Huh, sorry about that. Anyway, in theory, that would have given me, I'm not gonna debug that live. Cool, so just 5 minutes left, which gives me time to talk about time travel, which, so it's kind of a debugger, but it's kind of not as well. There's another reason I think why people do printfs a lot rather than say reaching for the debugger, beyond just laziness, which is that the debugger doesn't tell you what happened, right? And that process of debugging is thinking back in time to figure out what happened. The debugger tells you what's happening, right? But if you have time travel debugging, then you do get to see what happened. And this is a demo I like because it actually combines some of the kind of cool stuff of GDB as well. So I have another version of that bubble sort thing that we saw earlier, which does contain a bug. So if I run this like enough times, oh, that's not very clever. It will eventually crash. Come on. Right. Yeah, that's, I mean, yeah, thank you. Yeah, you know, sometimes if I'm working at home in the evening and there'll be a little yes, and someone in the family will say, oh, did you fix it? No, I made it fail. Because that's like half the challenge, right? So that dumped to core, so let's load that up. Let's see if there's anything useful in that core file. No, nothing at all. I mean, I can probably sort of deduce from here that it looks like I've got some kind of stack smashing because I've got a segv and no valid stack, but why? So I'm going to load that into GDB. I'm going to start it. I'm going to put a breakpoint on main, and I'm going to attach some commands to that breakpoint. So now everything I say here is a set of commands that every time that breakpoint is hit will be executed. So I'm going to turn on recording, and I'm going to continue. And then I'm going to put another breakpoint on exit, because it usually completes successfully, and I'm going to attach some commands there, which is just a rerun. And I'm going to set pagination off, because pagination is just always annoying, and I'm going to set confirm off, and now I'm going to run it. Well, that failed really quickly. Usually it takes a bunch of, let's do it again. So it's going to just keep going until soon enough, maybe I'll regret this now. But I wanted to show you the kind of ping-ponging. So I've scripted really, really simple scripting of GDB here, right? But the point of showing this is, you can, if you've got these non-reproducible things, you can usually script it pretty effectively. All right, it's crashed. And if I look at the backtrace, well, yeah, that's definitely not right. I can, but I've enabled recording here, so I can reverse step I, which is going to go to the previous instruction that executed. So I want it to tell me what happened. And yeah, sure enough, let's go into TUI mode. That's kind of looking like what I expected. So it's, actually I can look at the disassembly, and it's at this ret instruction here on x86. It's a fully descending stack. So the stack pointer should contain a valid address to return to. If I look at that, look inside that does not look like a valid address, right? So yeah, stack pointer is garbage. So my question is now, well, how did that happen? Well, I can just set a watch point on, I think I have to do this. The details of this you can look up later, but that's a location-based watch point to the top of the stack. For really annoying reasons. Look away now, but I just have to set, can use that, right, you didn't see that. Right, and now I'm going to reverse continue, so I'm going to go back in time until the instruction that corrupted the top of my stack. And it didn't. What did I do? What did I do wrong there? The nice thing about time travel is when you get it wrong, you can just go and do it again. So that was, that's off. Watch minus L. Stack pointer, reverse continue. Okay, I already got my expression wrong before. So yeah, a nice little demo in time travel, no biggie. When I got it wrong, I could run it again. Now it stopped when that array is being written, and I can say, what is array? and it's a 32 entry array, and that's the 35th entry that I'm trying to write into. So yeah, that is the end of the session. Thank you very much. I'm going to hang around a bit if anyone wants to ask questions or tell me if I missed their favorite thing or whatever. But yeah, thank you everyone.